Uh, Good morning again. My name is Sanggunan. I'm a PhD student from the School of Computing at KAIST. I'm glad to present my work in this conference. Topic of this presentation is on text entry method for smart glasses. Okay, now I start presentation, typing on a smartwatch for smart glasses. Smart glasses have advantageous feature for accessing information. Because each display is on user's eyes on, so that a user can be easily access to information from the device. However, because of its form factor, smart glasses is not a good input device. Especially text entry on the glasses is difficult to do. However, text entry for smart glasses is needed for various usage scenarios. For example, navigation application may require the text entry for searching location with the name of destination, and it is needed for texting with a friend, or also needed for searching information on internet. Therefore, previous researchers suggest text entry message on a various input space. Speech recognition-based text entry is one promising option. However, it can be hardly used in public space because may not be socially acceptable, and also there is privacy issue in speech input. Moreover, it is not accurate in noisy environment. Another option is typing in the media space. Media typing is not dependent on the form factor of the device, so it can be a good option for typing for glasses. Tracking a finger in the real-world scenario is one of the technical challenges for media typing, but even if we ignore the technical problem of finger tracking, it is also may not be socially acceptable and possibly occur physical fatigue because the user has lifted the user's arm in the air. And even if the form factor of the glasses is not proper to use a touch-based text input, touch-based input is reliable to use in any environment. Therefore, some researchers try to design typing on the frame of glasses, which has long and narrow form factor. But we should be considered that it is also may not be socially acceptable and occur physical fatigue because the user lifts the user's arm onto the frame of glasses. Sorry. And using an external device such as coding keyboard is also a proper option for easy and fast text entry. But in case of handheld device, a user should be paid attention to that he or she carries the device or not. However, if we use a wearable device as an external input device for the glasses, a user does not be paid attention to that he or she carries the device, and because it is one of the user's body. Especially, we suggest to use smartwatch, which is most popular wearable device, and also positioned at socially acceptable to interact and easy to accessible. Thereby, we present the concept of typing on a smartwatch for smart glasses. To say it short, I will call it in TOS in this presentation. To prove the concept of TOS, we conducted an online survey to compare perceived acceptability of three possible text entry posture. We gathered 125 respondents from university community. Each participant responded about three questions per postures. First one is perceived physical fatigue, and second one is willing to use in private space, and the third one is willing to use in public space. And before responding three questions, they saw the demonstration video about each postures, as shown in this video. First one is the typing on the touchpad on the glasses, and another one is video gesture. In the demonstration video, we will be making 10-finger freehand typing, and the other is TOS we presented. And this is a visualized result for the survey. About the perceived physical fatigue, TOS was rated as looks most comfortable. And about the willing to use in private space, Midair was preferred than TOS, but TOS was preferred than touchpad on glasses. Finally, about the willing to use in public space, TOS was most preferred, and also only TOS was positively rated. And next, we designed and implemented TOS in practice. First, we considered the design rationale of TOS. Considering the smart glasses provides the look-forward viewing experience, looking at the smartwatch for typing is the least burden for a user. And also, if a user should be looking at the smartwatch for typing, it occurs visual attention switching frequently between the glasses and the watch. It can be a negative factor for seamless interaction in smart glasses interaction. From these reasons, we use the smartwatch as an indirect eyes-free input device in TOS, just eyes-free for smartwatch. To make a smartwatch as an indirect eyes-free input device, we consider two possible options for that. First and straightforward option is designing a target-agnostic text entry. So we first implemented a target-agnostic text entry for TOS. From the previous study, target-agnostic text entry for smartwatch had been designed by CHANEL-R, which is called the Swipeboard. Hence, we used the Swipeboard as a first implementation for TOS. Swipeboard is two-page text input with using swipe gestures and tap gesture. At the first input page, a user should be select a target region along the nine split regions as shown in the figure. A user can select a region with a directional swipe or a tap. To select a region positioned at center, the region is containing FGH. User can do tapping gesture. And the other regions mapped to directional swipe gesture. For example, if a user do swipe gesture with upper right direction, the region positioned at upper right direction from the center was selected. And the second gesture can be a left and right swipe or a tap as a similar manner of a first input. For example, U is mapped to left swipe gesture, and I is mapped to tap gesture, and O is mapped to right swipe gesture. And this video is demonstration of a Swipeboard. Skip some. Oh, sorry, video is not working. Sorry. And the other option for TOS is designing a user can select a target without seeing the watch. To implement this option, we newly designed the text entry method. It is called HoldBoard. HoldBoard is designed from finding in the previous in-wild observation study, Smartwatch in Vivo by Pizza et al. In the Pizza et al.'s study, they mentioned that stabilizing finger on the watch allowed greater accuracy. Zoom in the picture is a stabilizing finger. The stabilizing finger may help to increasing accuracy by stabilizing hand posture, but we guess that kinesthetic sense between the stabilizing finger and an interacting finger also could help to increase accuracy. In succession, we assume that kinesthetic sense between the fingers may help to accurate selection even if a user do not see the watch. Hence, we designed the HoldBoard with the stabilizing finger. HoldBoard also utilizes the stabilizing finger to reduce the input complexity of the index finger. To do this, we installed 3 touch sensors on the side of the watch body, and each 3 touch sensors are absolutely mapped to the these three split regions in the keyboard. For example, if a user touches the thumb on the middle positioned touch sensor, the middle positioned region is selected. This is first input page of a HoldBoard. Then while the zoom is holding on the touched position, a user can select a target with the index finger. Touch screen position is also absolutely mapped to position of the inner space in a selected region. As shown in the picture, that finger position is mapped to this inner space in the selected region. When a user touches the index finger on the screen, a cursor appears at the mapped positions on the keyboard. The cursor is provided for novice users who do not yet achieve the kinesthetic sense between the fingers. A user can be adjust finger position if the user fails to touch the target. Finally, a character is entered at releasing the index finger, as shown this. Then also it is the video for demonstration. As you can see, while the zoom is holding at the edge, index finger can tapping to select a keys, like this video. Then we conducted experiments to evaluate two design options of TOS in seated condition and working condition. First experiment was conducted in seated condition, as shown in figure. We recruited 12 participants, and the study was split into 4 days to evaluate the techniques without excessive fatigue. Task was sentence transcription. As a result, text entry speed of a holdboard was reached to 10.24 WPM, and swipeboard was reached to 9.08 WPM. Then we conducted micro-analysis to show that target selection can be done without seeing a cursor on the keyboard. To show that we measure dwell time, we define dwell time as a time interval for which a finger lands on the screen and leaves the screen for a key selection. And the cursor is only appear while a finger lands on the screen, so therefore, dwell time means time to see visual feedback on screen. To determine criteria to interpret the result, we referenced Collier et al.'s study, which analyzed the mean dwell time of a key selection touch on a screen keyboard in wild. Determined the criteria marked as red lines in this figure, do not depending on visual feedback. Then this figure shows that dwell time per participant and per days. As a result, most of our participants can select a target without seeing the cursor on the keyboard, except one participant in the picture P2. So we show that it can be selecting without seeing the cursor. In succession, we conducted the evaluation as a further study from the previous study. In this experiment, we measured the performance of holdboard and swipeboard in both of seated condition and working condition. This study conducted with 8 participants who participated in the previous study. And the results show that text entry speed of holdboard show 10.85 WPM in seated condition and 9.02 WPM in working condition. And the text entry speed of swipeboard was show 9.10 WPM in seated condition and 7.666 WPM in working condition. Actually, the results show that much faster than we anticipated. However, the results clearly faster than typing on glasses technique. First, we compare the TOS with typing on glasses itself. Now, so I compare the result of swipeboard in TOS and swipeboard in typing on glasses. Swipeboard in TOS reached 9.08 WPM, while in typing on glasses reached 7.14 WPM, even if the task may be easier used with a 5-letter word input. Swipe journey in typing on glasses reached similar speed to swipe word in TOS, but in case of hold word, showed almost 70% faster than swipe journey in typing on glasses. And this is the one-dimensional handwriting. In one-dimensional handwriting is work for designing handwriting-like gesture input for text entry. In case of one-dimensional handwriting, text entry speed of letterwise input was not reached 5 ppm. So we can say that TOS is one of the promising options for smart glasses text input. Okay, then I will finish my presentation with summary and conclusion. In this paper, we first presented the concept of typing on a smartwatch for smart glasses and showed its perceived acceptability with online survey. Then we designed 2 design options for TOS, holdboard, and swipeboard. And finally, we presented evaluation research of 2 design options in seated condition and working condition. Thanks for listening.
Thank you very much. So, any questions? Don't forget to state your name and affiliation if you have questions. Nobody? Okay, so I'll fire a question at you. So you did this survey at the beginning where you justified basically the use of a smartwatch and you compared it to mid-air text input.
Yeah.
So I'm wondering in that survey, did you specify the conditions of mid-air input? Because you could think of more subtle ways of entering text, so maybe not typing conspicuously in the air, but you could do something more subtle with just one hand next to your leg, like using finger movements, or you can use the IMUs of the smartwatch.
In case of the Twiddler, we think that the handheld additional devices that are target comparison for our work. So we do not compare handheld coding keyboard. Do not compare handheld keyboard in online survey, and also in in case of mid-air typing, we choose this gesture for non-expert of HCI period. So it means that if a participant do not know any other mid-air typing gesture, they hardly imagine that how it work for typing. So we choose that.
Ready? Okay, so let's thank our speaker.